Hello, my name is Frank Blum. I'm from Oklahoma State University, and today I would like to tell you about our research on tightly bound polyvinyl acetate adsorbed onto silica. We want to answer a question: is it different from bulk polymer, and how? My co-workers are Hamid Mortazavian and Bunta Heteroyatin. On the slide, you'll see a schematic representation of a polymer, in this case adsorbed onto fumed silica. What you see is a couple of polymer molecules that are drawn with areas in the blue, green, and red. And these areas are polymer segments that have slightly different physical properties. If we look at this polymer, we can characterize it through differential scanning calorimetry. This turns out to be temperature modulated differential scanning calorimetry, and on the slide is the derivative of the heat flow curve for bulk polyvinyl acetate. What we see in the curve is that a glass transition is apparent, and it is moderately narrow, about 10 degrees wide, and occurs at the bulk glass transition temperature for polyvinyl acetate. If I take and add just a tiny amount of polymer and I add it to the surface of silica, what I see is a very tiny or no caloremic behavior. In other words, it just looks like baseline. As I increase the concentration a little more, what I see is that now there is some thermal behavior that seems to occur in the region of 60 to 80 degrees. As I increase the polymer amount a little more, I see that there's more of it by the time I get to about 1 milligram per meter squared. And then when I'm up around 1.12, I see a peak that looks like bulk polymer. That's what we call loosely bound polymer. And this loosely bound polymer has behavior that's similar to the bulk polymer. This loosely bound polymer is what I would show in the green region here. As I add more polymer, now I see that there are polymers that behave like they're in the red region. They're actually more mobile. These more mobile polymers tend to be at the air interface, and if I add a little more polymer to the sample, what I see is that for practical purposes, the intensity under the tightly bound polymer regime is roughly constant. The mobile polymer region is roughly constant. In other words, the substrate interface is fixed, the air interface is fixed, and what I'm doing when I'm adding more polymer is adding more loosely bound or bulk-like polymer. So this loosely bound polymer is different, and there are three distinct kinds of behaviors that we see. One of the things that we can do is we can add bound material to the surface, and we can actually estimate how much bound material we have. Here in the red squares are the amounts of bound material from the differential scanning calorimetry experiments. The bound material, or the fraction of bound material, is calculated by saying that there's a set amount of tightly bound polymer, and then when I add more polymer, the polymer that I add is loosely bound. You can see that the squares fit the line, or the experimental data fits the model quite well. A similar model is also shown for polymethyl methacrylate. In the case of polymethyl methacrylate, there's more tightly bound polymer than there is for polyvinyl acetate. On the lower portion of the curve, you'll see similar kinds of calculations for FTIR, and FTIR shows a much smaller amount of bound carbonyls. In the DSC case, we're looking at segments which tend to be motionally altered. In the FTIR case, we're only looking at carbonyl groups which are directly hydrogen bonded to the surface, and consequently, there's a smaller amount of bound carbonyl groups than there are segments which are motionally altered by the hydrogen bonding of the carbonyl groups to the surface. We have done a variety of other experiments on the surface, and what we have concluded from these and other studies is that the hydrogen bonding to the silica produces a tightly bound polymer. There are three distinct regions of behavior for the tightly bound polymer, loosely bound polymer, and mobile segments. The tightly bound polymer for polyvinyl acetate has a glass transition that's 25 degrees higher than bulk and much broader. We can quantify how much tightly bound polymer there is, and it's about 0.8 meters squared per milligram. If you want just a rough guideline, this represents on the order of 1 nanometer thickness of material. This tightly bound polymer also has some interesting properties. In particular, if you try to put plasticizer to lower the glass transition of the tightly bound polymer, it won't work because it doesn't go in. And we have used computer simulations to identify some of the details of the hydrogen bonding and also the chain packing in those systems.